In this video, let us see all kinds of load acting on the cantilever beam, how to calculate shear forces and bending moments, and how to draw them. So this is the question directly. The draw shear force and bending moment diagram of cantilever beam loaded as shown in the figure. Now you can see the single cantilever beam carrying combination of loads, point loads or concentrated loads, uniformly distributed load, and uniformly varying load, UDL, UVL, and concentrated load. Let us try to find out these shear forces and bending moments, and we shall draw the diagrams also. So let us right away find out shear forces. So as from the beginning we are habituated to calculate from right to left, so let us continue with that. So if I calculate shear force at B, FB will be 0 because there is no force acting on that. FC, so we have one force acting on acting at the point C, so that is downwards according to sign convention, that is positive, so that is positive kilonewton. You can see so all links for all videos are mentioned in the description for your kind information. Okay, FD, so shear force at point D, so there is no load in between C and D, right? So that 5 kilonewton will be continued up to there, 5 kilonewton. Now shear force at E, so as we know, shear force is the sum of loads up to the point we are considering on the beam. So up to E we have from the right two loads 5 kilonewton, and this is the 5 kilonewton is a concentrated load, and this 2 kilonewton per meter is a uniformly distributed load. So we have two loads. So one is positive 5 kilonewton plus uniformly distributed load 2 kilonewton spreaded over 2.5. So in order to find out the load, we have to multiply the load with the distance, so that that can be converted into concentrated load, 2 into 2.5. So we will get it as 10 kilonewton. And now shear force at F, shear force at F. So there is no load in between E and F, so whatever the load that is up to E, that will be continued up to F. So directly I will write it as 10 kilonewton. Next, shear force at G, we need to find it out. So at G, up to G, so we need to calculate the sum of forces from the right, whatever is acting, right? So up to G we have one concentrated load, one uniformly distributed load, one uniformly varying load. Okay, right, this is 5 kilonewton we have, plus this 2 kilonewton spread over 2.5 meter. So we are just summing up all the loads. So as this is a triangular load, so we need to find out the area of this triangle, that will be the load, point load, that we can be converted, that is actually representing the point load if it is converted to. So that we need to take the area of this triangle, that is half into base into height. Half into base is 3 meter and height is 4 kilonewton per meter. So we will get it as, upon summing up, we will get it as 16 kilonewton. And we need to find out shear force at H, the point H. So again we need to sum up all the loads from the right up to up to H. So that is 5 kilonewton plus this UDL spread over 2.5 meter, that is 2 into 2.5, plus this area of this triangle, that is uniformly varying load, half into base into height, plus 4 kilonewton. So you can directly add to this 16 also, but in order to make it clear, I am telling all this. Okay, that is total, you will get as 20 kilonewton. So let us write all the shear force values we have. So FB we have 0. So I want to rub this, so I will write all these here. So all the loads are written here, all the shear forces are written here. And here one more thing I need to say here, shear force at A, shear force at A is 20 kilonewton, because there is no load in between H and A. So that whatever the load at H, that will be continued up to A. So that I have written here. So those are all the shear forces. So let us now rub all this, and we shall try to find out these bending moments. Let us calculate the bending moments. So at point B, let me say MP. So that is 0. There is no load. There is no distance. So at C also 0 bending moment, because so what the bending moments we are calculating all are negative, because all the loads are acting in this manner on the cantilever beam. So all loads are trying to bend beam like this. So according to sign convention, this is actually hogging, so which is negative bending moment. So as a trick we have remembered, so this is crying negative thinker, so negative bending moment. So let us, if you see in that way, so shear force, bending moment at C will also be 0, because there is no load in, of course there is the load 5 kilonewton, but the distance is 0, because it is acting at C itself. So that is also 0. So we have the load, of course, 5 into 0, so that will be 0. We know bending moment is the sum of moments up to the point we are considering. Moment is nothing but force into perpendicular distance. So for your reference, I'll write it here. Moment is force into perpendicular distance. Distance perpendicular to the force. Okay. So MD we need to find out. So we have one force multiplied by distance up to D. So we have 5 kilonewton multiplied by distance 1.5. So that is a negative bending moment. 5 into 1.5, you will get it as minus 7.5 kilonewton meter. That is bending moment at D. So let us find out bending moment at E. ME. So we will get it as, so up to E we need to find out. So we have how many loads here? One 5 kilonewton concentrated load and one uniformly distributed load. So let us try to find out the force into multiplied multiplied by perpendicular distance up to E. So that is nothing but minus 5 into, so the distance we have 1.5 plus 2.5 up to E. 1.5 plus 2.5 minus, we have this uniformly distributed load. So force, that is 2 into 2.5 is the force multiplied by, so if you convert into point load, that is acting exactly at the center, as we have discussed earlier. 2.5 by 2, yes, up to E, that is the distance. So we will get it as, yeah, just a minute, we will get a minus 26.25 kilonewton meter. So upon calculation we will get it near to that. Okay, you please check whether the calculations are right or not. So the procedure is perfectly right. Okay, if you find out the bending moment up to F, so we have again 5, the load is 5 kilonewton multiplied by perpendicular distance up to F. So that is minus 5 into 1.5 plus 2.5 plus 1 meter up to F. I will write it here, 1.5 plus 2.5 plus 1 minus, so this 2 kilonewton spread over 2.5 meter, that is the force multiplied by perpendicular distance 2.5 by 2 up to E, that is 2.5 by 2, because it is acting at the center, middle. But we need to take the distance up to F, as we are calculating the moments about F. Okay, that is plus perpendicular distance up to E plus distance up to F, 1. We will get it as 36.25 minus 36.25 kilonewton meter. Now shear bending moment at G. So again in the same manner, so we have 5 kilonewton, added distance is 5 kilonewton multiplied by the distance 1.5 plus 2.5 plus 1 plus 3 up to G. So I will write it here, 5 into 1.5 plus 2.5 plus 1 plus 3. So that is this load into distance. We have another load now. This is minus 2 kilonewton multiplied by the distance it is spreaded over multiplied by distance, perpendicular distance from the center. So that is centroidal distance is 2.5 by 2, that is common up to E. So now we have to add the distances up to G. So that is 1 plus 3. 1 plus 3. We will get it as minus 72.25 Newton meter. So that is the bending moment here. Now we need to find out bending moment at H. So again in the same manner 5 multiplied by distance up to H. Now I'll write it as 1.5 plus 2.5 plus 1 plus 3 plus 2, that is the distance up to H. This total distance up to H minus this load multiplied by perpendicular distance. Load itself is 2 into 2.5. Sorry, a small correction here. So I forgot to add another load here. So let me drop this off. Yeah, sorry, I'm very sorry for that. So I have forgot to add the UVL also here. So let me do it again. Yes, so we have this load. So up to UVL you have. Just a minute, please. Yeah, okay. So this UVL we have it as minus. So we have to calculate the area of this triangle that represents the force, half into base into height, 3 into 4 multiplied by centroidal distance, that is, so centroid locates for this triangle at h by 3, I mean at base by 3, 3 by 3. So from tail it is 2h by 3. I hope you are aware of it. So even from our previous discussions. So of course the answer is correct. That is 72 point minus 72.25 kilonewton meter. Okay. Now let us find out this bending moment at H. So again we have one load 5 into distance up to here. I will write it quickly. Please bear with me. 1.5 plus 2.5 plus 1 plus 3 plus 2 minus 2 into 2.5 into 2.5 by 2 plus 1 plus 3 plus added distance up to H, that is 2, minus half into base into height is the area load, half into base into height, that represents the area of this triangle, as well as the UVL converted into point load, multiplied by distance, centroidal distance up to G, that is nothing but 3 by 3, but we are calculating up to point H, so plus distance up to H, that is 2 meter. We will get it as 90 minus 98.25 kilonewton meter. The procedure is right, so you just check out the calculations. So no problem with the calculations, but if you have the procedure, that is a very good. So up to A we need to find out now 5 into the distance up to A. So I will write it quickly. 5 into 1.5 plus 2.5 plus 1 plus 1 plus 3 plus 2 plus 2 minus 2 into 2.5 into 2.5 by 2 plus distance of A, that is 1 plus 3 plus 2 plus 2 minus, this is the area UVL. Area first we need to find out, take the force, half into base into height, that is the area representing the force of this UVL, multiplied by centroidal distance. Centroidal distance up to G is 3 by 3, I mean the length by 3 plus distance up to A, 2 plus 2. So ultimately we will get it as 140 minus 144.25. So let me write, so I want to rub this all in order to draw the bending moment and shear force diagrams. I will rub this off and write all the values here, right? Now all the points, all the bending moments and shear forces are written here. Let us try to draw these two diagrams. So let us first draw the reference line. Sorry, this is the reference line. Let me drop all the points A, B, C, D, E, F, G, H. So let us try to draw the diagrams. Shear force diagram. At B it is 0, 0. At C it is 5 kilonewton, 5. So there is no load up to C. So that 0 will be continued up to C. At C suddenly 5 kilonewton is being added as a shear force, and there is no load in between C and D. So that will be continued up to D. So that is of course 5 kilonewton. So at D there is no load. At E you can see 10 kilonewton. It is 10 kilonewton. And you see this is UDL. So as we are calculating the force into distance, we have taken the force multiplied by the distance it is spreaded over. So that uh, so initially I said F is equal to say small w into x, which represents y is equal to mx. The represents the straight line equation. So as the load is uniformly distributed, so there is a variation is there like this. So you have to join these 2 points with a straight line. And you can see there is no load in between E and F, so that 10 kilonewton will be continued up to F. And again at G, so how much were 16 kilonewton, and here that shear force relationship is diagram relationship is parabolic, if you remember, 16 kilonewton. So you have to join with a parabolic curve, and there is no load in between G and H, so that 16 kilonewton will be continued up to there. And at H it is added 20 kilonewton, and there is no load in between A, so that is 20 kilonewton will be continued up to A. So ultimately that is positive shear force. Positive shear force. Sorry, it was stuck, I think. This is positive shear force. This is shear force diagram. Now let us try to draw the bending moment diagram. So again draw the reference line. So drop all the points A, B, C, D, E, F, G and H. So let us mark all the points first. At B the bending moment is 0, at C it is also 0, and at D it is minus 7.5 kilonewton meter. Minus 7.5. So I am not representing the units. So here all the units are mentioned. So this is minus 7.5 kilonewton meter, and at E this is minus 26.25 kilonewton meter, and at EF this is minus 36.25 kilonewton meter, minus 36.25, and at G it is minus 72.25 kilonewton meter. At H this is minus 98.25 kilonewton meter, and at A this is minus 144 point. So that is the maximum bending moment, 4.25 kilonewton meter. So this is so now we have to join all the points. So this is we are joining with a straight line here, and there is no load in between C and D. You can join with a straight line. The bending moment of uniformly distributed load follows parabolic law, so you have to join with a parabola. And E and F there is no load, join with a straight line, and uniformly varying load, it follows the cubic law. So cubic curve you have to draw, and here in between there is no load between G and H. Draw with this join with the straight line, and this is the point load, and there is no load in between, no variation of load in between H and A. Join with the straight line. So that is the bending moment diagram. So the diagram is not very beautiful, please do adjust. This is negative. So this is bending moment diagram. So that's it. I hope you have got an idea on how to calculate the shear forces and bending moments on varying loads, a combination of different loads. Thanks for your time.